Okay, looks like it's working. Are we waiting on anyone that you know of? No? Okay. So, I'm Brady. I was told to do this about a week ago, so I did my best to prepare a presentation, but I might be missing some things, but feel free to ask me questions at the end. I started robotics with an FRC. That's at the high school level. I don't know how many of you guys have seen it, but it's the big robots. They're about the size of like a little bit bigger than like a small kid. And on that team, I was the lead programmer, and this is my second year mentoring FLL teams. So to start, hello? Thought it went out. So actually, there's a fair bit more phases here. How many of you have done FLL before, or some form of coding? Either one. Okay, a lot of you. Cool. Are most of you like in your first, third, fourth year, something like that? Or have any of you been doing it longer than that? Longer than 3 years? No? Okay. So for the newer teams with programming, what I would actually suggest before you start trying to tackle the missions and start trying to get your robot to go through all that, I would actually go through some generic tutorials. There are some that come in the Spike Prime app that you use to program your robot. Going through those generic tutorials are going to help you get an idea of how the robot behaves. If you're trying to design your robot and program it for a mission, and you find out later on that the robot doesn't actually behave perfectly. It's not a perfect robot. Like the guy in the last presentation was saying, these are plastic robots. They are plastic parts, happen to have some electronics inside, and they're not going to be very precise. So you want to get an idea of how they behave before you start coming up with some missions. And those generic tutorials in the Spike Prime app are going to be great for that. But once you do have an idea of how the robot will behave, what I would suggest is planning the path for your robot. Go ahead and plan the path that you want your robot to take. And there's a lot of ways to go about this. One of the most important parts, though, is that you try to find a way to make sure your robot is facing the way you want it to be facing and is actually located where you want it to be located. So at the very start, backing up your robot up against a wall, side of a robot, up against the wall, is going to guarantee that it starts off facing the same direction. And let's say from here, you were to come over to this mission. There's a line right nearby. If you guys are familiar with light sensors, you can have 2 of these light sensors. You can use that to line up here. If you come in at an angle, you can program it so that whichever one it sees, whichever light sensor activates first, you know that the robot is turned in the opposite direction from the side it's on. Does that make sense? Okay. And so from there, you know you can back up, rotate a little bit, and go forward again. And you can repeat that until both of these color sensors hit the line, notice the line at the same time. I didn't get enough time to get up any pseudocode for that, but if you have any questions about that, please let me know. And then there will be another tool you can use, and that is called the gyro sensor. It's built into the hub, so you don't need to add any extra parts for that. There is a simple way of doing it, which is to before the robot starts moving, you use the block called set yaw to 0. That's just the yaw is just the angle of the robot, and you set it to 0. You tell it to start moving. Using the wait until block, you would say wait until the gyro sensor is greater than the angle you want it to be at. But there's going to be some problems with that. If you've tried it before, you know that it's probably going to overshoot that angle, and it's not going to be very consistent. So there are a few ways to mitigate those problems. The first one, you'll notice that it's consistently overshooting its set point. It's consistently going past the angle you want it to be at. So you can just set that wait until block to trigger much earlier than the angle you want it to. So if it's supposed to be going to 90, and it's ending up going to 115, then you could set it to 75 degrees. And a second way that I suggest is staying in control of the acceleration. So you don't want it to just immediately put full power into the motors. That introduces a jerkiness. And if you accelerate smoothly, and there's in Spike Prime, there's a block. Who here is familiar with the extra blocks that you can add? So in the bottom, okay, all right, cool. There's a fair amount of you. So in the bottom left corner, there's an icon with the blocks and a plus button. When you click on that, it gives you a ton of options for even more blocks to add. A lot of them aren't necessary, but there's going to be, what you'll find is a more movement section. And by adding that, you actually get a block which allows you to set the acceleration of the drive base of the robot. And if you set the acceleration to slow, it will very smoothly ramp up the speed and ramp back down at the end. So when you're planning your missions, I highly suggest that you print these out, or some kids are actually would prefer to edit like the PDF on a Chromebook. A lot of schools will give kids Chromebooks, so if they're bringing those in, they could edit it on a Chromebook if they prefer. And there's a second sheet which is available, and it gives you some grid lines. Something that I was doing with my team is I took a ruler, which looks like this. You can fold it. I'll have a link to where you can find this stuff in a moment. You can fold it, and in the center here, it lists some angles. And with that ruler, you can actually measure the distance that you're wanting to go and the angle that you're wanting to go just with one tool. And it gives you a good initial estimate. The likelihood that your robot's going to go exactly the right distance the first try is pretty low, but it gets you that initial estimate. It saves a fair bit of time, especially with how I thought. Or with that tool, you can also figure out how many centimeters on the ruler equals 20 centimeters on the piece of paper, and you can do it without actually having to have the field in front of you. I would imagine most of you probably have your fields already, but if you didn't, then that would be a great way to get started and start planning before you actually have that field ready. And here I have a link to where you can find the PDFs for those two fields. That's what. login page? It does. Let me. Shouldn't force you to log. Oh. Okay. Yeah, on my laptop it was going to the right place. Let me see something. So these things I was able to access without logging in. Let me see. Yeah, for some reason on my laptop it goes straight to the link without any issue. So no, I'm not. So yeah. Okay. Okay. Well, I do have another link. So if you want to, oh, forgot I'm not on that page. Just a second. Here it is. Okay. I do have another link. If you liked that ruler, I really like having that one tool which is basically both a protractor and a ruler. If you want to get that, there's a link where you should be able to buy some. Yeah. Yeah, exactly. And you can even get a. You can actually take that piece of paper there, and you can actually measure what the angle of the model is relative to the field. So. Before I move on to some of the actual code, do you guys have any questions about what I talked about? Okay. So when a lot of what I see from kids when they're starting out, kind of what their first instinct is to do, and then it's also mentors that maybe aren't familiar with coding, is they'll find these movement blocks. There's one which says, hey, you can set the movement motors to C and D or A and B, whatever, the ports on the hub. And then there's a block which says how far the robot would travel with one rotation of the wheel. And then they would go on to make the robot drive around with code like this. So how many of you, just looking at this, could tell me what the purpose of this code was? What did... Okay, sure. Mm-hmm. Right. So, but it's very you can't really see how far you're trying to move. It's hard to see uh, just how much you're rotating just by looking at the code. So let's say one of your teammates that worked on this bit of code last week is sick. You can't talk to them about it, but this is an important piece of code before you can move on with the robot design. You could move on to something else, but if you're running low on time, then you'd have no choice but to go through and try to figure out exactly how all this works. So there's a couple things that I like to do. There's a few things that I like to do to try to clean up that code and make it much more readable, even for someone who normally isn't trying to, who likes to stay away from the code. The first one are custom blocks. I might be able to. How many of you can actually read what the text on the screen? I don't mean the code, just the text from where you are. Okay, so it's difficult to read. Okay. So here, the first thing we can notice is that with the previous code, there's a lot more blocks. There's a lot more blocks going on there. Whereas over here we have, so the pink blocks on the left over there would do the exact same thing as these red blocks over here. But with the red blocks, you can actually read it like English. When I receive mission 1, so when I'm doing mission 1, move forward 33 centimeters at 75% speed. Pivot around the left wheel 45 degrees at 50% speed, and so on. You can read that, a lot like English. And the other part of this is the broadcast function. That's the when I receive mission 1. And hold on. Zooming before so within Spike Prime, in that sidebar where there you have the operations, you have sensors, you have movement, motors, all of those categories. There's a category called My Blocks. What the My Blocks does, when you click Create a New Block, it's going to bring up a screen which gives you a few different options. You can create a text field. You can create an input. So with each block, you could create a block which says move forward, and then the input would be a number. And that number could be different each time you use the block. So you're creating your own blocks. The reason why I like those is they're reusable. It takes a function which you use all the time, such as driving around, and allows you to have it easily readable block. And then the broadcasts, the way I like to use them is to segment my code into different parts. They kind of act like a title for a specific portion of code. So the way you would do a broadcast is from, so under when program starts, you could say broadcast message, whatever that message is, you can name the message. And that would go to a block called when I receive message. And everything under that when I receive will be run. Now there's two different broadcast blocks. The first one will broadcast the message and move on. That one allows you to run two sets of code in parallel at the same time. That's really useful when you're trying to square up with a line, trying to line up with a line, because you can drive forward and you can tell one of the light sensors to, you can have a wait until block detecting both of the light sensors at the same time in two separate broadcast blocks. Does that make sense? Yeah? Okay. And then the second type of broadcast block is going to be broadcast and wait. The way I like to use those is, like I was saying, segment to segment my code, break up my code into different parts, more easily readable, easily digestible parts. So I'll have a broadcast mission 1 and wait. So I'll wait for everything in that to finish. Or I can even break up a single mission into multiple parts, depending on how complex it is. So here I have some very basic examples of what you might do with a custom block for driving. It doesn't employ anything. It doesn't employ the gyro. It doesn't employ any light sensors or anything like that. But that should get you started. Since some of you are taking pictures, I do have a disclaimer there. I created this last night, I believe. That's when I got all these images put together. I haven't had time to test that, so that may not actually work. But this is the general concept. In here, I figure I might as well point out comments. Comments are very important, even though some of it might be human readable. These other parts here, some of this code, you may want to put in a comment saying what that math is doing. So for these rotate blocks, what we have, I'm going to come over here. You have rotate right, and then I added an input called degrees. Degrees acts a lot like a variable. And you can drag it, you can just click on it and drag it into a spot just like you would with one of these variables. And so whenever you use one of these blocks, you can put in a number here or letters as well, and that will be input here. So this code, like if you had to rotate left 120 degrees, this degrees variable would become 120. And then what I did with the math to actually make sure that it's rotating the correct distance, and remember this is without gyro, is I took the circumference of the wheel. How many of you are familiar with what circumference means? Okay, cool. So I took the circumference of the wheel, and I took the distance between the two wheels. So when you're rotating, the two wheels follow a path. Do any of you guys know what that path is? When you're rotating, just rotating in place, the wheels are going to follow a circle. So if you rotated if you made one full rotation, the wheels will be right back where they started, right? Okay. So if you do half a rotation, then it will rotate like this, and one wheel will end up where the other wheel was. And if you trace that, that looks like a circle. So what you can actually do is, using the circumference of the wheels, you can find out how far it will travel per rotation, and using the circumference of that path that's traced by the wheels when rotating, you can figure out how far the wheels need to go in order to rotate to a certain angle. Does that make sense for you guys? I'm sorry, I couldn't hear that. Oh, okay. No sensors at all. Not even the gyro. This is like a very rudimentary way of doing it. If you're having trouble with getting the gyro to be reliable, then this might be a way to do it. This is the way we did it the first year because we wanted everything to be very simple. Trying to implement a whole bunch of new techniques is going to be very difficult, and can end up spending a lot more time than you think on it. And here's another way that I like to use. So here's kind of demonstrating how I use broadcast blocks. So I'll have a when program start. The very first thing I run is basically a reset of everything. I want to use variables here, like wheel diameter and wheel base, so that I can rotate the right amount. And I want to set these values right at the beginning, because I don't want to have to plug in those values every single time I want to use them. Because if any time that changes, you change wheels, change any of that, get a little further apart, anything like that. If I miss any of those values in the code, because I don't, when the robot stops working, it might take you a while to find where along the line did you plug in the wrong value. So anyway, the very first thing I like to do is a reset, and I keep that segmented, or I keep that away from the other code, so it's easy to see. And like here, once again, use of comments. Down here, I just say, hey, this is the pi times wheel diameter, and that gets me how far the robot moves with one rotation of the wheel. So after I do that reset, it waits until the reset's completed, then it runs mission 1 once everything is ready. And then, oh, I didn't include the picture here. But I also had a celebrate thing. It just flashed a smiley face on the hub. All right. Do any of you guys have any questions? Still have a little bit more, but okay. So I don't have a whole lot for you here, but this is something called PID control. This is what you would use if you are ready to try to improve your usage of the gyro. If you're a brand new team, I probably wouldn't suggest going for this. What this is instead of just rotating until the gyro equals a certain number, what this is, a simple way of doing it is to cut out the I portion and the DE portion. So just focus on this first part right here. And what that's going to do is it's going to take your error. So how far away are you from the gyro? If you want to rotate 90 degrees, then your error will be 90. And then you'll have a constant number. This is a value that you would tune depending on your robot. It's going to be different for every robot. And you would multiply it by that error. And what that would result in is, at the very start, the robot would move quickly. It would move pretty quickly. And then as that error gets smaller, it would go slower and slower until it finally meets its set point, until it finally gets to that 90-degree rotation. And that P constant is something that you'll have to tune. If it's too low, then your robot will take a really long time to get to that 90-degree angle. Or it may not even get there at all. If it's too high, what you'll find is it will overshoot. Then as it overshoots, it's going to try to come back. And if it's really high, it'll oscillate. Your robot will just oscillate back and forth. So it'll keep rotating back and forth, back and forth. So what you're looking for is a robot which quickly goes to 90 degrees, maybe overshoots a tiny bit, depending on the situation, because sometimes I can make it a little bit quicker, and stops. You don't want any oscillation. And then the next two portions are important if you want to do line following for curve. if you want to follow a curved line. So that first part, where you just multiply error by some number, the robot will not react quick enough as it's trying to follow this curved line. So there are two other portions. I'm actually going to go over the last one first. So what this is, instead of error times some constant, it's going to be your change in error. So if your robot's moving perfectly straight, and it's following this line, and then it curves, it suddenly curves, that will cause the error to change very quickly. And when the error changes, that's when this gets used. If the error stays the same, this actually ends up being 0. But when it changes very quickly, it tries to combat that. So if the line suddenly curves, then the robot is going to apply even more power into turning in that direction. Or if, let's say you want to set a really high value up here so that it can get to its set point quicker, but we know that will oscillate normally or overshoot, this will see that the error is actually decreasing really fast. It'll see that the error is decreasing really fast, and it will slow down the robot so that it doesn't overshoot. Do those two parts make sense to you guys? Do you have any questions about that? This is a fairly advanced topic. Most of the places you go to learn about this will talk a little bit about high school and like college math when they're trying to explain it. So I just want to make sure that I explain this clearly here. Okay. This middle one is something that you probably won't have to worry about unless you're trying to push your robot to go as fast as possible. The difference with that is it takes the total sum of error over time and multiplies it by some constant. So the longer that the robot is not facing or is not following that line or facing the direction it wants to be, the more power it will apply to correct that. So if you have something, if let's say one of your wheels is going much slower than the other for whatever reason, like I was saying before, these are not perfect robots, not perfect materials. That will happen. This part will notice that the robot has had a lot of error, and it will correct for that. Am I going over time? Oh, okay. Sorry, I wasn't sure. So that is, oh, I do have one more slide, but do any of you have questions about how you might be able to use PID control? No? Okay. Well, there's one other resource that I wanted to give you guys. This link should work. It's just not going to a Microsoft thing. This will go over a lot of programming principles, some principles with building a robot as well, because building a robot and coding goes hand in hand. If you're building a robot, if your design isn't rigid, so when it moves, it kind of wobbles or anything like that, then it's going to be very difficult to program. So they go over how to build a robot that's easy to program. It's going to be some tutorials on various concepts. They go over some basic concepts. They go over some much more advanced concepts, from PID, like I was talking about, to how to follow a line, use the gyro, and all of that. All right. So this is my last slide. So I'd be happy to take some questions. If any of you are experienced in FLL and want to step in if I am explaining anything wrong, then please do. But if you have any questions, feel free. Now's the time.
Hey, I'll step in a little bit. So my name's Jared. I am Rhonda Rawson's husband. A lot of you get emails from my wife. She's the program delivery partner for FLL. I used to coach FLL. I currently coach FTC. You did a great job as a programmer. I can tell. Not all of you are programmers. I can tell by some of your questions that you didn't quite follow what he was saying. So what I do at work, I work for Boeing. A lot of times I have to translate programmers to management. And so I am going to, if you go back to where you were showing the program for how to use measurement of the wheels to turn or drive straight, I'm going to explain that a little bit differently. So he spoke to you the way a programmer does, all about the variables and stuff, which is awesome. But at its heart, this is actually a sensor-based system. It's just not a sensor that you had to plug in, other than you plugged in your motors. So internal to your motors, there is actually a little sensor. It's sensing how many times that motor shaft has rotated, right? Now that little tiny shaft coming out of your motor, it's a little tiny thing. It's going to rotate a whole bunch of times. Depending on what size wheel you attach to that shaft is going to control how far your robot travels. So if you put little tiny wheels on there and you rotate that shaft 10 times, it's going to go a little distance. But if you put great big wheels on there, it's going to go much farther, right? That's what this program is really doing, is it is measuring how far you're actually traveling when you rotate a motor. And that's a really important concept in FLL. One of the first things I always get my students to do when I was coaching was create a my block that says drive straight for X inches. So that means you have to know how many motor rotations cause you to go an inch. That's really easy. It used to be really easy to do with the EV3s. You could just put them in a little display and it would show you the motor counts. You have to kind of capture that information through the program in here. But once you figure it out, after you've built your robot based on how size of your wheels, how far you can travel, make it go out a foot and find out how many rotations took you to get out that foot, and then divide by 12, right? That gives you how many rotations it would take to go 1 inch. Turn that into a my block. Now you can reuse it everywhere. You can go back, at the very beginning, he was showing you the mission planning. What I always did with my students is we always started with that mission planning. I wouldn't let them code until they had a plan, right? And I always kept a tape measure there and a piece of paper. And I said, all right, you come up with a plan of where you're going to go from the end here, out here, turn here, and get there. I like how the previous speaker talked about using your finger on the models. Show me what it's going to do. I did the same kind of thing. You take your finger and you trace the path along the route that it's going to go, right? And then you write it down. Okay, I'm going to drive straight. How far? Get a tape measure. Measure it out. Now you've got that. You put that into your my block. You could write out on a piece of paper your entire mission and get that robot right there. Now all you have to do is work on your attachment, right? To interact with that model. But that's what he's really doing for both driving. You can do that with both driving straight and turning. So same thing, same concept as how many rotations does it take to go forward. If you set one wheel going one way and one wheel going the other way, there's a certain number of rotations that equals a 90-degree turn. By 90, now you can make a my block that says turn 6.2 degrees. I always found that's actually, back in the EV3 days, the gyro sensor was extremely unreliable, and we could smoke anyone trying to use a gyro sensor with that my ball. Because that motor is turning so many times, it's a very precise turn. And then his advanced concept with the PID, that is really advanced stuff. We use that in FTC all the time. But if that seemed confusing to you, get the basics down and then go to YouTube and search FLL PID control, something like that. You'll find all kinds of videos so you can start learning with it. And it's all about the same way you would do as a person if you were driving around and you saw, hey, my car is kind of drifting off to the side. Well, I'm going to push it a little to the left. If I push it too far, oh, now I'm going too far, now I'm going to pull it back. It's the same thing. You're auto-adjusting. That's what you get the robot to do. I want it to go straight. I'm going to use that gyro sensor. See if am I drifting off? Okay, I'm going to put a little bit more power on the right wheel. That's all it's really doing. I just wanted to make sure everybody understood that. Cool.
Yeah, thank you.
Open it up for more comments, questions.
From what he was saying, it sounded like he might have noticed that. Is it possible that some of you didn't understand what a variable was? Do you guys know what a variable is? Do you guys know why I used a variable? Okay, I'm not seeing quite as many nods. So let's say instead of variables, I used numbers. So in both of these places, and I have more my blocks than this. I think. So out of 8 my blocks, we have a ton of numbers. There's 2 reasons why I use the variables. One, you can read. You can just read it. It says wheel diameter. Instead of reading a number, like 5.6, you don't know what that number is unless you've been working with the code. So instead, here you can read wheel diameter. And the other reason is when you use a larger wheel, that changes the distance that the robot travels per rotation. And so if you ever decide that you'd rather use a larger wheel, because that would increase your speed, then you could change the variable, and it would change everywhere else. So I think most of you guys said that you've done FLL or coding before. So there's a couple no's, but I've seen a fair amount of nods. What have you struggled with before with programming? What has been weird? What hasn't behaved the way you thought it might? Ah, yes. Mhm. Okay. So there are a couple ways to tackle that. First is where you're placing it at the very start. I'm sure you guys spent a lot of time and got really close down to try to line it up with the lines. Yep, you're trying to line it up perfect. So one thing you can do is actually make a little Lego jig. Like you could you could put together some Legos that you push up against the wall, and that would, and then you could push your robot up against that. You did? Okay. So, what were you using to get your robot from one place to another? Were you trying to use the gyro, or were you just telling the wheels to move? Okay. Okay. So another one of the things is making sure you're not going at full speed. If you're going full speed, it's if it bumps into something, it's gonna knock it off course way harder than it would at slower speeds. And at full speeds, you're pushing the limits of those motors. And when you do that, the differences in the motors come. I remember how I was saying the motors are very different from each other. They're not all made exactly the same. When you push them hard, those differences come out. One wheel will be going slower than the other. Okay. Yep, that's actually pretty good. So, and then there's one other thing you could do without sensors, and that is, so you're lining up with the wall in the beginning, and with the jig. But if you are ever, like, in the middle of a mission, or in the middle of getting to where you need to go, if you end up near a wall, or if you know the robot's going to be close to a wall, then you can actually purposely have the robot drive into the wall so that it lines itself up. Did you ever try that? Once? Okay. Okay, so an important part to be able to do that is to have a flat edge that the robot can push up against. A flat piece of Lego, fairly wide, ideally at least as wide as the hub, probably wide. And this piece is not like a crucial piece for any other reason but to push up into a wall. It's its only purpose. So that way, if when you're bumping it, you're not bumping the sensors. You're not knocking the sensors out of place. You're not bumping any other parts in your build. Okay. Then I saw you had your hand up as well. Mm-hmm. So the what are your guys' field set like at your home practice field? Do you have is it a lot like what you have at competitions, or is it just a map? Okay. So in that case, it's going to be if it's different enough from the way they set it up at competitions. If you're not following the exact way they set it up at competitions, then what you end up doing is you're lining up everything for a field that you're not going to ever play on. That's not a good way of putting it. You're lining it up against a piece that won't be there. You're lining up against a wall that's in a different spot. And even just the slightest difference can make a very big difference. And if that wall is just at a slightly different angle, Or if anything is different there, then that can end up causing some problems. Yes? From the real competition tables? And so that's where some of those other techniques come in, like with the gyro. Figuring out, making sure your robot stays facing the right direction of the gyro. While you're moving forward, one thing you can actually do is if you notice the gyro is not at 0, you set the gyro to 0 when you start moving forward, and it's not at 0 like while you're moving forward, you can actually tell the robot to add a little bit more power to one of the wheels, or start trying to turn a little bit until it gets back to 0. Yeah? Python? So in FLL in particular, I have not used Python, but I've done programming in other situations. And for example, comparing if we were to compare Scratch to Python, do you guys know what Scratch is? Okay, if we compare Scratch to Python, Scratch just has these blocks. It's a very limited set. Scratch is actually built on what's called JavaScript. JavaScript, you have, if you were to write everything in JavaScript, you would have full control over everything. And it's also going to actually run the code faster. So this code, what it does is there's loops. It's running in a loop. That's what it's doing. And the faster that it can loop, the more accurate it will be. And if you're using Python, then actually run those loops faster than it will with the blocks. But there is a big downside to that. If you're not used to reading lines of text like that, if you've never encountered, if you've never used Python or JavaScript or anything like that, it's going to be a big transition. So you want to make sure that most of your team is on board with that, for one. Two, I would probably make sure that you have some mentors that are familiar and are willing to help out with that. But if you have that and you really want to explore it, then I don't see why not. But I haven't, just so you know, I have not actually used Python with FLL specifically. Okay? Yes? No, we use Java. So Java and JavaScript, even though they both have Java in the name, are two completely different. So yeah, I used Java and FRC. Mm-hmm. Probably. You would probably be able to learn it easier. And there's another thing. In FRC, there's another option, and you can actually use Python in FRC. It's been developing for the past few years, and they are just now officially supporting Python. So by the time you get into FRC, that's going to be a very viable option. So if you get used to Python with FLL, as long as your FRC team isn't already using Java, they don't already have a bunch of code written for it, because when you're in FRC, you reuse code. There's a lot more code than you're doing in FLL, so you're going to be reusing that. So as long as they don't already have a ton of code in there, feel free to do Python. I don't have anything else, so if you guys are done, that's okay. But I don't mind staying here if you guys want to talk or ask any questions. Was there anything up here that you guys wanted to see before you go? Okay. So there's also, here's the link right here. So if you write this down, can you see it? Okay. Yeah, so if you write down that link, it'll take you to it.